Okay, this is Unit 8, Target 1. Working with perpendicular bisectors, really in a triangle, but we're going to start with just perpendicular bisectors. Try to move this out of the way. Okay. So Target 1, perpendicular bisectors. So I have drawn a segment AB with a bisector that's perpendicular going through point M. I used M because I wanted that to be my midpoint. And so I can tell that this is a perpendicular bisector because I have the congruent marks showing that AM is equal to MB, or segment AM is congruent to segment MB. And then I also have the perpendicular. So it's a perpendicular bisector. Here's what we know. We know that if we put any point on a perpendicular bisector, so if I call this point C, or if I do another one, point D, it says this in words here, any point on a perpendicular bisector is equidistant from the endpoints of the segment. So what that means when I drew point C, that means that CA is going to equal CB. If I wanted to show that, I could draw a segment and put a mark there, CB, put a mark there and show that. I could do the same thing with point D. I could say that AD is equal to BD. And so I could draw a line there and show that congruence, and draw a line there and show that congruence. So what I'm going to do right now is kind of erase the green lines I just drew so we can focus on why that works. Again, why does a point on the perpendicular bisector, why does it have to be the same distance from both endpoints? Okay, so if we look at the triangles that are there right now, you have one big triangle ACB. You got that perpendicular bisector going through point M and also point C. And so that creates two smaller triangles. Well, just using the red marks that you see, we have AM and MB. So I'm going to draw out this triangle, AMC. We know AM is congruent to MB. We know that angle M, or AMC, and the angle M on the other triangle, angle BMC, are both right angles, and we know all right angles are congruent to each other. And then both of the triangles share segment CM because of the reflexive property. Those are congruent. So essentially the two smaller triangles, AMC and triangle BMC, are congruent triangles. Once I know that they're congruent, I can say that any of their corresponding parts are congruent. Well, this segment, AC, and this segment, BC, are corresponding parts. So those have to be congruent because the triangles are congruent. And all this, again, shows this point, that any point on a perpendicular bisector is equidistant from the endpoints of a segment. The converse to that theorem is also true. If we know that those two segments are congruent, if we know CA equals CB, that tells me that the point C is on the perpendicular bisector. Here's some example problems of what that looks like. A couple of these are from the notes from class. I'm going to start up here. I'll call this number 1. Focus on number 1. What is SR? What this part of the diagram is trying to show you is that SQ is a perpendicular bisector. You see the perpendicular symbol. You see the little tick marks to show that Q is a midpoint. Okay, if I didn't have the tick marks to show congruence, I wouldn't know that Q is the midpoint. And so what they're telling me is that Q, or SQ, is a perpendicular bisector. Or more specifically, they're telling me that point S is on the perpendicular bisector. Well, my theorem says that if a point is on the perpendicular bisector, then it is equidistant to the endpoints. And so if SP is 6.8, then SR is also 6.8. For number 2, I have the converse. This time they showed me that I have a perpendicular, but they did not show me midpoints. They also showed me that 24 and 24, that kind of drowns out the 24. Let's see. I'll just use the tick marks. They show me that the 24 is on both sides. In other words, what they're showing me is that H is the same distance from E as it is from G. Those are congruent lengths. Equal lengths, congruent segments, which means that H is on the perpendicular bisector of the segment, EG. And so if this part is 9.5, then this part is also 9.5. Example 3 that I have down here is actually showing something that's not a perpendicular bisector. My question is, why is B not on the perpendicular bisector? And what I meant to draw in there was that those two bottom parts are still congruent. So in this triangle, I see that there is a midpoint. And the answer to my question is not that I don't see the box for the perpendicular. The answer to my question is using the theorem. And so I know that B is not on a perpendicular bisector. It's on some kind of bisector because it is on that line, and that line through B intersects the midpoint of segment AC, so it is a bisector. But because these numbers are actually different, 4 is not equal to 5, that tells me that B is not on the perpendicular bisector. So that's a couple different logical ways to look at what a perpendicular bisector does. All right, moving along. What we then learned is that because a triangle has 3 sides, and each side has a perpendicular bisector, all 3 of those perpendicular bisectors are going to intersect at a point called the circumcenter. So down here in my circle, this point in the center of the circle, is called the circumcenter. And what we looked at in class is that we can move the triangle around, and that those 3 perpendicular bisectors, these are all perpendicular and bisectors, okay, all 3 of those perpendicular bisectors will always have a point of concurrency, which means that they will always intersect at a single point. Anytime 3 or more lines intersect at a point, it's called a point of concurrency. And this one is specifically called the circumcenter because it's the center of a circle that goes around the triangle or circumscribes the triangle. And what that tells me from the bisector theorem, remember, any point on a bisector is equidistant to the endpoints. Well, the endpoints of my segments are all the vertices of the triangle, which means that the circumcenter is equidistant to all the vertices because it's on all of those perpendicular bisectors. So you can actually draw a circle around the triangle where you have a radius that can be drawn to each of the vertices. We know that the radiuses, in a circle are always the same length within a same circle. So those red segments that I just drew are all the exact same length. And that's true for every circumcenter. So here's a simple problem of a triangle. The perpendicular bisectors are drawn in blue. I didn't have some of them go all the way through the sides. And sometimes in your homework problems in the book, they might take this blue segment and they might only draw it to there to try to make it easier to see less lines in the triangle. They might take all your perpendicular bisectors and only draw them that much, but really they go as far as they want. You have 110 in red, one number 10, not 110, one number 10 in red, and that is the length from the circumcenter to the vertex. And so that means the length of every circumcenter to the vertex is 10. And so x equals 10. And that is how to work with target 1. The last thing I'll tell you is that there's a nice application that you saw in one of the notes from class. You might see it on a homework problem, that circumcenter, because it's equidistant from all the vertices, if you're trying to find a meeting place of 3 things, or you're trying to build something like I used the example in class of building a new bathroom outside around our sports fields. If I wanted to find a location that was in the center of, let's say, the baseball field, the stadium, and the tennis courts, I could find the circumcenter, and that would be the equal distance place that all those places could go to the bathroom. So that's a nice application.